Welcome to the pilot action of the New Metro project. The New Metro project aims to identify and support skilled workers in fourth-generation industry with an emphasis on training needs and emerging skills across Europe. As part of the project, the University of Ioannina, as a partner of the project, created a series of videos for the development of skills. This video aims to present the basic concepts around the Introduction to Formal Methods section. Introduction. A software engineering methodology resides on a development process which consists of several phases: analysis, specification, design, programming, unit testing, integration, and system testing, maintenance. Formal methods are appropriate for describing complex systems, appropriate for reasoning about systems, supportive to program development, provide assistance to a methodology. Static and dynamic analysis for testing. Static analysis of a program does not need code execution, performs a lexical analysis of the program syntax, and performs a check of the structure and usage of individual statements. This procedure is sometimes automated. Dynamic analysis of a program involves running the system to perform testing. The code runs formally under controlled conditions and the respective outcome is expected to be reached. It involves path and branch testing. Formal methods definition and reason for using it. Formal methods comprise techniques and tools which involve mathematics and formal logic. We can assume a variety of forms and levels of thoroughness. Less thoroughness incorporates the occasional mathematical notation put in specifications. The full thoroughness involves the formal specification languages with precise semantics. Formal methods are essential since systems are mostly dependent on software components, even in mechatronics. As such, embedded software in the industry exhibits high complexity. Also, maintaining reliability in software systems is quite difficult. Formal method concepts. There are formal specification methods which include formal specifications, formal proofs, model checking, abstraction. Formal specifications. It includes the interpretation of a non-mathematical description into a formal specification language. Succinct description of high-level properties as well as the practice of a system. Well-defined language semantics support formal deduction about specification. Specification types. Informal. Based on natural language. Ambiguity can result in incompleteness, inconsistency, and misunderstanding. Formatted. Standardized syntax. Performs consistency and completeness checks. Semantics that are not precise may result in other error problems that may still exist. Formal. Syntax and semantics thoroughly defined. Precise form, mathematics. Diminish lack of precision and ambiguity. Specification and implementation shows equivalence and it is verified. It can be difficult to read with lack of training. Formal specifications. The target is to describe external behavior of a system without constraining implementation. Formal methods include two parts. Logical theory, this the way that someone reasons about specifications, properties and programs. First-order predicate calculus, quantification over variables. Second-order predicate calculus, quantification over relations. Temporal logic. Structuring theory. Defines elements that are being reasoned. Formal specifications types. They are property-oriented whereby wanted properties are stated in a declarative way. Algebraic, the data types are considered in terms of an algebra. Axioms describe the properties of data types operations. Axiomatic, it uses first-order predicate logic pre- and post-conditions. The desired behavior is described by stating the model of the system. They are model-oriented, which provide a direct manner of describing system behavior. Sets. Sequences. Tuples. The model-oriented formal specifications includes the abstract model, in terms of previously defined mathematical objects. Also, the model-oriented formal specifications include state machines. Algebraic specifications, property-oriented. The algebraic specification uses input-output assertions. Sets of operations. Axioms which are dictating behavior of operations. Two parts to a specification syntax. Axioms. Abstract model specifications, model-oriented. Construct an abstract model of the desired software behavior with mathematical types, sets, relations. Definition of specific operations by showing impact of the operation on the model. The specification includes the type of model, invariant properties of the model for every operation, name parameters and return values, pre- and post-conditions. Formal proofs. Complete arguments for the validation of some property of the description of the system. Constructed as a number of steps, each of which is justified from a set of rules. Diminishes ambiguity and subjectivity when moving to informal conclusions. Model checking. The procedure is operational and not analytic. We have a state machine model of a system which is stated using a formal language. The model checker checks if the state machine satisfies the requirements stated with formulas and a logic. The basic method is to explore all the reachable paths in a computational tree which originates from the state machine model. Abstraction. Need to simplify and put aside non-relevant details. Need to concentrate and generalize significant properties and characteristics. Avoid early commitment to the design and implementation selections. The program and a mathematical object. The program is equivalent to a mathematical object. The programming language is equivalent to a mathematical language. We can prove properties regarding the program. Formal specification language. It originates from formal mathematical logic rules, in conjunction with certain programming language additions. Type systems, parameterization. It is non-executable and designed to specify the computing entity and not how the computation is to be achieved. Most formal specification languages are based on axiomatic set theory or higher-order logic. Specification languages features. The primary feature is for the language to maintain explicit semantics. It needs to have a mathematically secure foundation. It needs to have expressiveness, flexibility, convenience, economy of expression. It needs to include data types of programming language records tuples. Specification languages features. It needs to have an easy-to-use syntax. Also, it should include diagrammatic notation. In addition, it should include strong typing. It can be richer than programming language. It provides economy and coherence of expression. Checking provides stability checks. Total versus partial functions. A plethora of logics assume total functions. Subtypes can assist to making total functions flexible. Specification languages features. Axioms and definitions. Axioms can include incoherence and should be utilized sensibly. Definitional principle ensures that definitions are well established. Some languages use type checking conditions to be proved that will be generated to ensure good definitions. Modularization. Separating a specification to modules is very important in terms of organization. Parameterized modules allow reusability. Specification languages features. Built-in computation model. In order to omit simple type checking constraints. Strength and proof checking. Maturity. Documentation. Tool support. Associated literature. Libraries of proven specifications. Measure of standardization. Formal specification logical errors. Logical inconsistency, which essentially constitute the easiest errors to be detected. Accuracy, which checks whether the specification mean what it is meant. System invariance help in the detection process. Completeness, which established whether the specification identifies the contingencies and specifies the desired behavior for all the cases. Peer review can help in the detection process. Detection of formal specification errors. Thoroughness and application cost dictate the following error dictation techniques. Formal specification inspection, which is done manually. Syntax correctness parsing, in an automatic manner. Type checking for semantic consistency in an automated manner. Simulation based on specification, automated as well. Theorem proofs, proof checking, model checking for logical inconsistencies. Formal specification is system description. Establish specification requirements and high-level design. Express implicit assumptions. Locate undocumented and unexpected assumptions. Show problems such as flaws. Identify exceptions. Evaluate tests. Pros of formal specifications. Thoroughness provides a better comprehension of the given problem. Defects are found, which would probably pass without notice using traditional specification methods. We can identify problems and defects earlier in the product lifecycle. They can ensure the absence of certain problems/defects. Pros of formal specifications. Language semantics pave the way towards checking for self-consistency of a problem specification. Formal proofs are enabled that can constitute fundamental properties of the system as well as its invariants. Repeatable analysis dictates that reasoning and specific outcomes can be checked by colleagues. Pros of formal specifications. Provides a system abstract view concentrating on the output of the system itself rather than the way to produce it. The abstract formal view assists to separate the specification from the design process. Strengthens existing review procedures by examining with thoroughness. Cons of formal methods. They can be used as a tool to work together with quality assurance methods and not as a replacement. Care and skill are required in order to increase confidence in a product's reliability. Specification thoroughness cannot be assured even though it allows for consistency checks. Costs may exceed benefits, hence prudent applications is necessary. Formal methods and problem domain-specific knowledge must be fully integrated for the rigor of results. Conclusions. Formal methods are not the Holy Grail. They can detect problems and defects in the early stage of a product lifecycle. They can be integrated in an existing project process model. They can improve quality assurance when applied prudently to the appropriate projects. Thank you for your attention.